In this work, we introduce Hyperion, a fast, versatile symbolic Gaussian belief propagation framework for continuous time SLAM. With Hyperion, we not only establish a solid foundation for decentralized data estimation, but also resolve long-standing performance challenges associated with continuous time parametrizations. My name is David Hug, and I'm with the Vision for Robotics Lab at ETH Zurich. In conventional discrete-time SLAM, a robot moves along a trajectory while accumulating information about its surroundings. Here, this is illustrated by a drone capturing sequential images from which features can be extracted and tracked over time, yielding discrete pose estimates. Following this essential paradigm, several approaches exist in the literature that successfully deploy this strategy, resulting in accurate pose estimation algorithms like OrbSLAM-3. In addition to the obtained pose estimates, these algorithms also simultaneously reconstruct the observed environment in 3D, as shown in this video. However, one of the limitations of these pipelines is that they assume synchronized inputs and steady sensor acquisition rates, implying that these standard algorithms fail to fuse asynchronous sensor readings. While continuous time SLAM has addressed the fusion of unsynchronized sensor data by leveraging time-continuous motion parametrizations, distributed state estimation remains an open challenge with few solutions. This issue arises from the circumstance that existing SLAM algorithms predominantly rely on centralized non-linear least squares optimizers to solve the underlying minimization problem. These solvers, however, do not easily extend to distributed state estimation across multiple agents. Moreover, they omit explicit covariance estimation, which hampers the detection of diverging or non-converged states. Despite their advantages, splines also present significant computational challenges. Specifically, deriving their mathematical expressions and residuals is often tedious and error-prone, leading to suboptimal implementations and negatively affecting optimization performance. To address these challenges, Hyperion utilizes Gaussian belief propagation for distributed stochastic inference, while largely automating the code generation process itself. To this end, we extend SymForce to delegate the generation of performance-critical code. Conceptually, these extensions translate intuitive, high-level symbolic mathematical expressions into complex, highly optimized, low-level expressions with limited interpretability. Leveraging this approach, we benchmark our automated spline implementations against the highly optimized, handcrafted solution by Sommer et al. In the groups of 3D rotations and transformations. As shown in this table, the proposed method outperforms the handcrafted spline implementations by up to 2 orders of magnitude. These speedups are particularly significant given that residual and Jacobian evaluations are a major bottleneck in optimization performance. Aside from these performance improvements, Hyperion also reformulates the standard optimization problem as a stochastic minimization, representing it as a probabilistic factor graph as shown on the right. Framing the optimization as a stochastic process not only allows covariance estimation, but also enables the entire problem to be approached as a distributed state estimation based on Gaussian belief propagation. In particular, Hyperion leverages local message passing to incrementally update neighboring nodes and factors, propagating information throughout the graph in a decentralized manner. Combining the advantages of Gaussian belief propagation and continuous time SLAM, we evaluate the proposed algorithm in absolute pose and visual localization setups. The resulting sequential estimates across iterations of the proposed algorithm are visualized in these videos in magenta. Here, we also illustrate the estimates produced by Ceres alongside ground truth, which are colored in white and green respectively. Both the simulated and the real-world setup, which extracts the relative pose with respect to a Cheruko board, reliably converge to the same solution as Ceres. This observation also extends to the localization setup, where both approaches converge to the same estimate as depicted on the right. Here, the non-zero error arises from the perturbation of the landmark observations, rendering it more important that both solutions are identical rather than comparing the absolute errors themselves. To illustrate the convergence behavior a bit further, the estimates are also shown at initialization and after the first iteration. From this, one may observe that both methods take similar steps towards the ground truth trajectory after a single iteration. In addition, we also conducted an ablation study on the dropout ratio for the Gaussian Belief Propagation-based approach, where different colored lines correspond to different levels of dropped messages in the node and factor updates. That is, the probability that a send node to factor or factor to node message is lost. These plots illustrate that even under a dropout ratio of 60%, the Gaussian Belief Propagation-based approach converges to the same solution compared to the case where no messages are lost. We conclude our experimental section by investigating the impact of choosing different spline types. Here we specifically compared B and Z-splines, which are two closely related representations. The key difference between the two lies with the characteristics that B-splines are approximating, while Z-splines are interpolating. From these graphics, we conclude that the centralized Ceres solver is agnostic to the choice of spline, while opting for a Z-spline for the Gaussian Belief Propagation-based solver results in better convergence. As a result, the local convergence properties of Z-splines seem to be better suited for distributed approaches. In conclusion, this work introduces the first open-source Gaussian Belief Propagation-based continuous time optimization framework with symbolic code generation. Furthermore, it implements the fastest Ceres interoperable B and Z-spline implementations to date, further alleviating computational limitations. In addition, we demonstrate the efficacy and robustness of the proposed framework in absolute and localization setups, even under incomplete message passing. Lastly, Hyperion is also available on GitHub, offering a comprehensive open-source implementation.